Hello and welcome back. Now we'll be looking at Fpga design. You might recall from the introductory notes, the Fpga stands for Field Programmable Gate Array. That is a logic chip that you can buy that you can configure in your lab to perform a specific function. And in fact, you can implement designs equivalent to potentially hundreds of thousands of logic gates onto an Fpga. Now, in general, design for FPGAs is very similar to design to standard cell ASICs. Just about any RTL of a reasonable enough size for the particular FPGA you've chosen will fit into the FPGA and will map onto it. However, if you want to fit a large design into an FPGA, that is a design that stretches the resources of the particular FPGA you're choosing, then there are certain guidelines you can follow that will give you a greater probability of fitting that design in. And that is actually largely what this section is about. That is, how to make efficient use of the available resources in an FPGA so you can fit larger designs within one chip. So what I'll be talking about, I'll describe in detail the architectural features of common FPGAs, and then I'll talk about design techniques specific to FPGAs. However, largely those design features are making efficient use of the architectural features that are made available to you. Now, I've chosen in these notes to illustrate these issues with the Xilinx Virtex 5 FPGA family. However, I would say that I'm not particularly advocating one FPGA family over another or one FPGA brand over another. They all have their pros and cons, which are really beyond the scope of this class. So let's look generally at FPGA architecture. There are two major elements within a field programmable gate array. You have C or Bs, or configurable logic blocks, which have slices in them that allow you to build combinational and sequential logic of any form mapped onto those slices. You then have a programmable switch matrix that includes transistors operating as programmable interconnect that allows you to connect up the different CLB patterns within any format that you want in terms of the interconnect structure. So in general, the combinational logic and sequential logic maps onto the CLBs, and the wires in your design, or the nets in your netlist, map onto the programmable switch matrix. By having a large number of these arrayed across the FPGA chip, you can fit quite large designs within an FPGA. However, there's a general issue that we'll come to later in these notes, and that is how much logic you'll fit in is determined by how efficiently you can use the CLBs and the features within them. If you have lots and lots of wires, for example, so that you have to heavily use the switch matrix, you'll end up using fewer CLBs, and thus, in the end, fit less equivalent logic gates into your design. So we're going to look at the two types of logic slices available to make up a Xilinx Virtex 5 CLB. This is the logic M slice. M stands for memory because you can actually use parts of the slice as memories. We'll go through the structure here left to right. On the left here we have small SRAMs, 6 address bits, 2 output bits, 05 and 06. This allows you to build any 6 input, 2 output logic. You might recall, if you build a truth table for logic, that becomes directly equivalent to the programming of a ROM or RAM as a lookup table for that logic. So within this structure, you can fit anywhere from equivalent of 1 logic gate to quite a handful of logic gates, depending on the specific logic function that you're implementing. Now in the M slice, these SRAMs, you can see there's 4 of them here, can not only just be used as lookup tables to implement logic, they can actually be used as RAMs. That is, within the design, each of them presents 256 bits of random access memory that you can use to map as small custom embedded SRAMs. They can also be set up to be used as a shift register. Okay, so that's the 4 lookup tables / RAMs on the left-hand side of the slice. We then have some steering logic in the middle here, including these muxes. Very explicitly, part of the steering logic allows you to build carry chains. In fact, you can even see this is specifically labeled C in and C out. Then on the right, we have storage, very specifically for 1-bit storage elements. That can be configured in a number of configurations. They can be configured as flip-flops, latches, and SR flip-flops, that is set-reset flip-flops. What is not shown on this slice, in this diagram, is the overhead to actually program this for specific functions. The idea is that there are SRAM bits that control how these latches or flip-flops, storage elements, are set up. There are scan chains that allow you to load in the bits into these SRAMs to build lookup tables or ROMs. In addition, there are storage bits not shown that control the configurations of these RAM blocks that actually specify for their specific design whether it's a RAM or whether it's a lookup table. This programming overhead is not shown here. In fact, the FPGA companies keep it quite proprietary so that you can't reverse engineer how to program their FPGAs. But this is what the logic designer sees in terms of the structures here. The configuration bits are what's produced by the FPGA design tools that are then loaded in the FPGA in your lab to actually implement a particular logic function. So that's the M slice. This is the slightly simpler D slice. The only difference here are that these SRAM blocks on the left here can only be used as lookup tables or read-only memories. In fact, you don't have to change anything to use them as such. You build a lookup table into a read-only memory. There's still SRAMs. The lookup tables are still programmed by having logic not shown here, writing bits into an SRAM to implement a particular lookup table function. However, you as the designer cannot use them as SRAMs. You can only use them as read-only memories or lookup tables. Everything else here stays the same in terms of the steering logic, the carry chain support, and the 4 output 1-bit storage elements. So for example, let's say we have this RTL, and again, any valid RTL can be mapped into an FPGA. The only question is efficiency. Always at pos edge clock, E equals D or F. Well, as I think you've already figured out, the D or F aspect is loaded into the lookup table. And this is that table. I haven't shown how the SRAM specifically is programmed, but well, actually I have. This is these addresses. You're going to get ones programmed for the output 06. The output 05 is not programmed. And at the other addresses, all the other addresses within the ROM, you have zeros programmed into the memory. This is a lookup table equivalent to D or F. Notice I can fit more logic in here. I have another logical output that could still be programmed on top of this. Also notice that by only having one logic gate here, and this isn't meant to be terribly general, I basically built the equivalent of one logic gate using this 256-bit SRAM. Right. Then we have the steering logic that is set by external SRAMs that are not shown, going to the storage element, which in this case will be configured as a flip-flop, again by storage elements that are not shown. So this is a simple example of how the compilation tools will map RTL onto a piece of FPGA technology. Modern FPGAs have a lot of other hardware resources besides the configurable logic blocks and programmable switch matrix. For example, again, I'm focusing on the Vertex 5 family to keep this simple. They have larger memory blocks, 36 kilobit memory blocks that can also be configured as FIFOs, that is first in, first out buffers. And they also include things such as optional error correction circuitry. There's also DSP slicers within this particular FPGA family for supporting communications processing functions largely. For example, 18-bit 2's complement multipliers and adder accumulators. And many FPGAs have embedded microprocessors within them. In this particular example, a 7-stage in-order PowerPC microprocessors. The point of this custom logic that is used here, if it is useful to you, you should use it. And use it very directly with knowledge that these things are available for you. Rather than force mappings onto CLBs, which is a lot less efficient in terms of area usage. I mean, this one multiplier is most equivalent in area to a very small number of CLBs. Thus, if you have a multiplier and you can configure it as this 18-bit multiplier, you should do so. If you configure it as a 20-bit multiplier, then you'll actually end up using an array of CLBs to build that larger multiplier, which will take up a lot more area than this DSP slice, and furthermore will leave this DSP slice wasted. So a big part of you efficiently using an FPGA is simply to structure your code so that it can map directly onto the resources that are available. For example, if you have FIFOs in your code, build them as 36 kilobit or 18 kilobit FIFOs. Don't build it as a 48 kilobit FIFO if you can avoid it, because then a bunch of CLBs will have to be involved as well in order to map it onto the logic structures. So this is a quite simple lesson. Tune your design at the RTL to make best available resources, to make best use of the available resources. For example, these 18-bit arithmetic units, 256-bit SRAMs. If you don't build a slightly larger than 256-bit SRAM, map it onto 256 SRAM so you can use the M slices. Obviously, if you have software, build it into the PowerPC units. If you have adders, you saw a ripple carry chain there. You didn't see a carry look ahead chain. So build your adders as ripple carry adders. We'll point out that the total amount of embedded SRAM available in many FPGA families is limited, so you want to be very careful and efficient in how you use it. Furthermore, these FPGA vendors provide a lot of IP, that is existing designs or intellectual property. For example, they will provide you code for DRAM interfaces, Ethernet interfaces, and so on that has been tuned to their FPGA family. And you should use these codes rather than write them yourself from scratch. FPGAs also have configurable clocks and I/O resources. An example at the top here, again, Xilinx family, they have programmable clock trees. You can not only set the frequencies, but you can do clock gating, you can do other things like that. And again, to make this easy to use, the FPGA vendor provides Verilog templates that enables you to use them. FPGAs also have quite a wide variety of I/O available to the designer. For example, the general I/O can often be configured to operate at a variety of different voltages and using a specific interface standards. For example, some of the I/O can be configured very specifically to support DDR memory interfaces and the logic, the voltage, and so on standards required for DDR. In addition, the FPGA families quite often provide a number of I/O pins that are specifically designed to operate at very high data rates. For example, the Rocket I/O family within Xilinx can operate quite fast to do FPGA to FPGA communications. So if you need more than one FPGA, you can have a very fast channel or a set of very fast channels between those FPGAs. So they're the logic functions. You both have general programmable logic functions in the CLBs and specific logic functions to support various high-level operations, to support clocking and I/O. Next, look at the programmable interconnect. The ideas in general associated with each CLB is a set of wires around it, and of course wires to the CLB that are not shown here, that go to a programmable switch matrix. On the right, I show a diagram actually from one of our own papers on two different ways to build each bit of the programmable switch matrix. This is a 1-bit 4 input to 4 output programmable connection. There's two ways to build these. The way on the left, I have gates controlled by tri-state gates controlled by registers. The idea is most of them are in the high impedance mode. A few of them are set to transfer the input to the output. Those that are set to transfer the input to the output determine the direction and the connectivity of which of these pins is the input, which of these pins is the output, and their connection. Notice this is a 1-bit, 1 input, 1 output block. Another way to build these is again with registers controlling muxes and tri-state buffers, again to enable one input to, for example, go to one output by setting the select lines on the muxes appropriately and the states of the tri-state buffers appropriately. Notice this is very expensive. This is 1 bit at one programmable switch matrix. In general, you have many bits, and of course you can see you have many programmable switch matrices. So the interconnect is actually very limited in capacity. And this is an important issue in FPGA design. Also, it's going to be slow. As you transition each programmable switch matrix, you're transitioning 1 or 2 logic gates depending on the architecture that is used in the programmable switch matrix. Also, it's going to be very power hungry. A lot of capacitance associated with each bit at each programmable switch matrix. Thus, highly interconnected structures are not desirable in FPGAs because you'll quickly run out of programmable switch matrix resources and won't be able to connect up a lot of your CLBs. They'll be left empty simply because you run out of routing capacity to connect them up. In addition, heavily interconnected FPGAs will be slow and consume a lot of power. By the way, I think you can already see why FPGAs are significantly slower and significantly more power hungry than standard cell ASICs. It's because of this overhead required to have programmability in these lookup table logic functions, and in particular in the programmable interconnect. So again, here's a simple example. Here I've got 2 flip-flops, so I have to use my programmable interconnect because they're wired in series. G uses E. So, for example, D and F will go into one CLB through a programmable switch matrix. That will produce an output G, which will go through another programmable switch matrix to another CLB, which will also reuse F, which I haven't shown, in order to produce the result G. So this intermediate wire here is carrying E through the programmable switch matrix from CLB to CLB. So making efficient use of interconnect is very important to produce a high quality FPGA design. You want to favor designs, even algorithms, that favor logic over wiring. For example, if you're familiar with the fast Fourier transform, if you do a full 2-dimensional array of multiply accumulates to implement the fast Fourier transform, there's a lot of wires. So you don't want to do that. You want to build it as a one-dimensional architecture, as a simple pipeline, because there'll be a lot less wires in that architecture than in the full two-dimensional architecture. What this means in general is you want a physical architecture that goes from neighbor to neighbor, so you don't have a lot of long-distance wires that have to go across multiple elements. You should be able to draw your design as largely a pipeline design with neighbor-to-neighbor interconnectivity. This will map a lot more efficiently into an FPGA than a design with lots of random wiring that spans multiple logic blocks. You want to put logic next to the resources that's using it. And you want to be able to keep critical paths within one block and as close together in as small an issue as possible. And in general, you want to avoid high fan-out nets, because that will also use a lot of programmable switch matrix resources. Thus, in general, the less wiring you see in your architectural drawing, the better off you'll be in using the FPGA, and the less long-distance wiring in particular. Going down one more level of subtlety, a lot of FPGA families provide specific features that you can use to get specific benefits. And again, this often involves details in your code. For example, realizing that FPGAs are very power hungry. FPGA vendors have quote-unquote low power FPGAs. They're not particularly low power. They still won't get you down to the power levels of a standard cell ASIC, but they do reduce the power. So for example, the Xilinx Coolrunner family has a clock distribution that uses double-edged triggered flip-flops. The idea here is that if you use both edges of the clock, you can run the clock at half the rate. And since the clock is the big part of the power consumption, this reduces the power consumption of the chip. But you have to write your code to actually reflect this. So if you're using this particular FPGA family, you actually have to write your flip-flops with always at positive edge clock or neg edge clock. So you're using both edges. Again, these Xilinx parts, everything uses a synchronous reset. Thus, you want to program write your RTL using synchronous resets, not asynchronous resets. Some FPGAs have a lot of tri-states within the CLBs, and there's ways of using tri-states as muxes. Thus, if you want to mux, you might be better off programming it as a set of tri-state buffers. This actually doesn't apply to the Vertex 5 family. I'm illustrating, it's another one. Again, clock gating and things like that can be directly supported within the clock distribution tools. And also, in general, and very specifically within FPGAs, there's a very strong speed, hardware area trade-off. Thus, one trick you can always leave to the end of the design cycle. Let's say you've got a function, you're trying to fit it within one FPGA, and it doesn't quite fit. Well, what you'll often find if you relax the clock cycle time somewhat, because high-speed operation requires parallel logic implementation, you'll actually free up logic resources and thus are more likely to fit your design within a specific FPGA chip by relaxing the clock a little bit. So that brings us to the end of this section. The two main lessons I want you to take home with you are that the logic density of your design depends heavily on how you write your RTL. In particular, if you have fixed architectural features in the FPGA, write your RTL to exploit those fixed architectural features so they're not mapped, so your code is not mapped inefficiently onto large arrays of CLBs. In addition, so that you can actually use the available CLBs, try to minimize the amount of wiring you have, and in particular avoid long wide wiring runs, for example by going to architectures that communicate largely between nearest neighbors. Thank you very much for your attention.